Everyone, this is Shawn Oram. He is a lead mechanical engineer with Ecotope out of Seattle. So Ecotope is one of the leadership or engineering firms in our whole country in how to electrify buildings. Shawn has been a specialist in central heat pump water heaters, so he's presented on that previously with us. Today, he kind of begged off. It's like, I've already trained you how to do this a few times now. Let me talk about some of the other amazing things we're doing. That's what you get to see is like what's even more amazing than their leadership in central heat pump water heaters. So thank you, Shawn, for showing up and teaching us all. Take it away.
Yeah. All right. Can you guys see my cool background?
Yeah, it's like ripply water.
Yeah. Sorry, I had to do this, but that'll be the last time. Here
Well, yeah, Zoom doesn't really do it justice because it gets a little bit interrupted, but it's
Okay.
wonderful.
All right. Well, yeah, thanks, Shawn. So I'm going to try to not talk about heat pump water heaters. And as Shawn mentioned, I'll show you a little bit about some of our commercial work and kind of the work that's ahead for all of us. But the existing commercial field is ripe for upgrades. And so I'm going to tell a little story here. So here's a quick agenda. I'm going to go through some of the commercial building progress. And when I say commercial building progress, I mean the energy use of commercial buildings through the energy code years. And I'll show you kind of what we are finding up in Seattle. I'm going to also brief on a sensitivity analysis that we undertook with NBI. I'm going to present a concept designed for off. And I'm going to show you a couple of projects where we've implemented this and some of the results. So that's my goal. There's a lot of pictures, so I'm going to go fast. So to start out, we've got current commercial building progress. And the story here is that energy codes have made quite a bit of progress. We've essentially knocked down all of the internal gains inside of our commercial buildings by at least a factor of 2, if not 3. I'm showing 80 to 2012. This slide's a little dated, but it's even gotten more aggressive on the lighting. So this is an example of what's happened in 20 years. The energy code has also changed our envelopes. We've gone to much better, higher insulation levels. We've got single, we went from single to double and even triple now is sort of at market. And then we start to look at some of the studies that have looked at office buildings. So these are big commercial office surveys, CBEX being the biggest one. And that back in 2003 was an EUI of 93 kbtu per square foot. CBSA is a local Pacific Northwest, same kind of database office building, EUI 82. In the 80s, they did a study and the commercial office buildings were 75. In 2002 and 2004, they did another study in Seattle and we dropped it by 3. So that's kind of the story on the ground. So that's the existing building kind of case, the CBEX and CBSA. Those are already existing buildings, just a snapshot of what's there. Here's sort of the new buildings. So not a whole lot of progress here. And one thing to think about this is that there is significant grid capacity that lies in existing buildings. We have sort of honed in on if you can get a building down to about 30 EUI, I mean, you can do this pretty easily. And I'm going to try to show you that you can do this with this design for off approach that we've done. And I'll show you some examples. But if you look at the energy that's left above that red line, that is all the energy that is available in the grid that we could be releasing. And that's and we need to do that so we can make room for space heat and vehicles and heat pump water heaters. We embarked on a sensitivity analysis about 10 years ago with NBI, and it's really trying to understand what are the levers that impact your building energy performance and to what degree. And so that's what this study sort of set out to do. And really, there's kind of 3 pieces to energy performance. There's the design. So this is designers, architects, engineers. They kind of come up with the programming, the layout, and so they have influence on some percentage of the total outcome. We've got operations, so staffing, controls, how it's controlled, what the maintenance schedule's like, what commissioning. If those items slip, then you start to see that in the energy use. And then we've got tenants, and so tenants are really hard to control. Computers, equipment. We've got schedule. We've got different habits. So all of this is sort of centered around office building, but it essentially applies to most commercial buildings. So a little background on the sensitivity analysis. We used the NREL prototypes. This was really a deep dive into Mark Frankel's brain. He came to Ecotope and had this wild idea to try to understand where the levers are and where we can make the most impact. And so it was a really interesting study, and it informed us a lot in our design practice. But we essentially took the various parameters in an energy model, and we modeled a high case, a low case, and a base. And we wanted to see what the impact of each individual measure was, or lever. And so here's sort of what resulted in that. And this is a Seattle climate, so this is going to be biased towards Seattle, but there is a report that came out. It's on NBI's website. I've got a link here in this PowerPoint. But this sort of summarizes what matters, and you can think of each of these topics on the bottom as a lever. And and what we did is we modeled kind of the base case, which would be kind of like ASHRAE 90.1 across the 0% line, and then we swung it sort of an increment below and then kind of an increment above, somewhat aligning to ASHRAE 189, which is an efficiency standard for commercial buildings. And we can see that there's still a lot, there's kind of 4 different areas where the energy is. And so I'll give you an example of the envelope here. We've got air tightness, we've got glazing area and glazing U factors. So the report has all the different single glazing, this would be double, and this would be high performance double, somewhat triple. So you can see there's 5% total energy if we go to better windows. And then this becomes additive as you change the U factor, as you change the insulation levels in the building. There's another 15% there beyond code. Also adding mass has a significant impact. So this sort of highlights that we're not done with insulation levels. And obviously this is somewhat climate dependent, but insulation, we've still got a ways to go there. Sorry. And so the next piece is going to be kind of HVAC, and there's a couple highlights here. The HVAC sizing is really important. If we oversize systems, they tend to cycle a lot, so we get a lot of excess fan energy. HVAC system type is really important. That's this big bar here. One is a package single zone gas pack or heat pump. The one here, which is losing 20%. This is a big central VAV system, and then this is a ground source heat pump or a VRF. And we can see that this HVAC type has a pretty big driver on the energy use. The thermostat settings was another interesting one, and I think this is actually a really big culprit in a lot of buildings, along with big central air systems in terms of energy usage and trying to get this down. But the thermostat settings really comes down to the deadband between the heating and cooling. And if we have a really tight deadband, like we do in a lot of commercial Class A office buildings, we can see that this ends up being a lot of simultaneous heating and cooling to the level of about 35% additional energy just on that tight bandwidth. And a lot of systems are designed around this, especially VAV. And so when you can sort of move away from that and really extend the temperature band, or the temperature band point between when the heating is first triggered, or the heating set point, and the cooling set point. And so you want to get that as far apart as possible, so you eliminate the simultaneous heating and cooling. Sometimes it's not possible in commercial buildings, but it's a goal. And then finally, plug load. This one's pretty interesting. If you leave your computers on overnight, you're going to drive up your energy use potentially 23 to 25%. And so powering them off at night will give you pretty significant savings, but leaving them on is a lot of hours. And we see that in a lot of buildings. So
have anything on domestic hot water in that graph? Or I mean, you're an expert in domestic hot water.
Yeah, no, this is office, Sean, and office has very little domestic hot water. So it doesn't really even show up. It's just, mostly it's a lav. In office buildings, it's hand washing, lav sinks. There's usually not showers. There's not really much of a water load in commercial. That's not all commercial buildings. I'll show you a few that do have some.
Thank you.
Yep. All right. So design for off. What is this? This is a term that Ecotope coined about 10 years ago, and It involves a lot of pieces, and instead of kind of going through it, I'm just going to list it here. This isn't as elegant as I wanted to do it, but it's essentially there is a methodology to designing systems, and what this methodology is really about trying to design. It's a design approach that's focused on trying to turn the systems off by design. And so examples would be if you use high performance ERVs and HRVs in a commercial building, you will turn off the heating function and the cooling function of that outside air. That is a huge measure. And that is why, I mean, in Washington State, all of our commercial buildings require ERVs, DOAS ERVs or HRVs. So that's a huge measure. That went into code in 2012 in Washington State. Keep in mind, we are a heating dominated climate. The other piece to this is using smaller zonal systems for heating and cooling, and to cycle the heating and cooling systems on a call for heat, as opposed to running the fans continuous and big central air systems. And so the VRF is one prime example of this, also fan coil units, but individual zonal control where we don't have to turn on big central fans is a really good idea. And so that's paramount to part of the design for off, because we're turning off that main primary air supply fan. Opening up the deadband between the heating and cooling set points, you have to be careful here, but the greater that range is, the less simultaneous heating and cooling. And so that's what we're really trying to turn that part off. The right sizing, the larger equipment will short cycle, so we're trying to turn excess fan energy off. So you can see it's the same basic themes. Demand control is really turning off the ventilation air. Daylighting controls turns off the lights. High performance envelopes are used really to drive down the balance point. I'll explain that a little bit more, but this is really, that's the crux of the super insulation approach with commercial buildings, and I'll show you a couple examples of that. All right, so these are the case studies. This is the first one. It's RFM Office. RFM is Rice Fergus Miller Architects. They're in Bremerton, Washington, and they bought a 30,000 square foot old building in downtown Bremerton, Washington, about an hour west of Seattle, across the lake, as they say. They essentially came to us and said, let's try for a net zero energy building. So we helped them achieve, get close to this massive deep green retrofit. We ended up with an EUI of 19 for an office building. It's net zero ready, so the full roof of PV will cover it. It's 100% electric. It cost $105 a square foot to renovate the whole thing. LEED platinum and some rainwater systems. The architect coined it, we put a down jacket on it and turned it off. And that was Greg Belding, Rice Fergus Miller. But I think that pretty much nails it, what we did here. I'll show a couple more slides. Here's the building in its dilapidated state. This is Steve Rice, the principal. So we embarked on an energy model and really tried to attack the load reduction measures. So we super insulated, kept the glazing down, and installed heat recovery ventilation. The HVAC systems are VRF based. We did not use a heat recovery version of VRF. We used just a heat pump mode. I'll tell you why in a second. Energy recovery ventilators were used. We've got a big 14-foot big ass fan kind of central to the project. We've got a natural ventilation scheme that we call passive mode, and that's powered on by red and green lights. So when the lights are green, everything turns off and the building just opens up. It's very low tech. It's just it's kind of users or operators will power the windows open as they desire. Here is what we call a bin analysis. And so this is the 9 to 5 p.m. bin hours. And bin hours would be in a full year, essentially how many hours are there in this temperature range. And so this will help to describe a climate. So between 45 and 50, there are 450 hours at that range. And so that then defines kind of the work you have to do in the wintertime to keep the building comfortable. And so I'll kind of explain what we did here is we've got a blue zone on the left, and that's when it's 45 or lower. We've got this kind of temperate zone, 45 to 55. We've got this passive mode, and we've got this heating mode, which is shown in the red. And so the idea is that we are only really using the heat pumps for about 30% of the year. The other 70%, we've got a natural ventilation scheme, and we're using ERVs only. We use the VRF heat pump to essentially turn the system off in this primary core 70% of the year hour. And so by turning the VRF system off for 70% of the year, we see pretty tremendous savings. Here's a little cross section of the building. The architects, Rice Fergus, did this. And essentially, it's a big box. It's well insulated, R50 roof, R30 walls, R40 floor. And we've got a giant destratification fan sitting in the middle. We cut a hole through the floor. And so this fan essentially ventilates everything. And they use it to kind of destratify the space. And also during big events, they turn it up and they can cool this entire space with no mechanical cooling. So that's kind of what we are after, off, turning off the mechanical cooling. Here's a kind of a shot of the inside of the space. So the architect's offices are here and here. The operables are here. These are manually opened by this lever, and then this fan can be adjusted, turned off, but this will spin. The architects love it. It's super comfortable. Here's getting into the weeds a little bit, but so we looked at some of the bills afterwards, and we've got a tool we've developed called TERM. It's a temperature energy regression model. What it does is you feed the energy bills in and the weather files. It will align those, and it'll tell you when you've used energy at these certain temperature bins, here's what's happening to your building. So it'll kind of take your EUI. So your base load EUI is about 21 down here. And as it gets colder out, we can see that the EUI starts to rise. And so during the heating season, the EUI is 28 and 29 up here, 35 degrees outside. But what the important part about this is it'll show you just by looking at the bills what the balance point of the building is. So the balance point of this building is somewhere around 53. The balance point is simply the temperature outside where your building first needs to turn the heat on. And that's really kind of an important factor. Here is kind of the proof in the pudding. We've got our annual energy use. We've got a very serious M&V system on this project. We have essentially over-geeked the amount of data we have. But it was really, we did this to really understand, what the impact of all this installation and this kind of off approach was. And so we can see it's a pretty flat curve. This building costs about 25 cents a square foot a year to operate. And we've got a little bit of heat that occurs in December and January, and then some warm up on the swing seasons, and then a tiny bit of cooling. But the rest of the time, this building just opens up. So we can see the impact of turning systems off. We've got lights as the green. We've got fans, very minimal fans. We've got some heating as the purple, and then cooling's this tiny little blip here. And then the solar production is here. There's a 9 kW array on the top. All right, that's the first one. The next one, this is a new construction project. This is Fire Station 72. It's located in Issaquah, Washington. This was built in 2010. This is an all-electric building. It's a 2-story, 3-engine station. It's got a geothermal heat pump. It was super optimized to minimize the size of the geo heat pump. And it came out an EUI of 23. This is the lowest energy station in the US, or the one that I've seen. TCA Architects were the architects. This is kind of breaking down the approach, but really we worked with the city of Issaquah, and they wanted a net zero energy fire station, and so we started to dive in and try to understand the problem. We set up an energy model to try to match an existing station up the street, so we could really understand where the loads were. So I'll explain some of that, but essentially we tried to understand this problem. Big focus on load reduction. So this is super insulation and energy recovery ventilation. Passive technologies wherever we can use them. Recovery and reuse. The rainwater is a big piece of that. It has a rainwater for toilets and laundry. And then the mechanical and the lighting system efficiency is very important. And then PV would be kind of the energy generation portion. So that was the basic approach back down. This is the kind of the result of the end use
Sean,
breakout. Yep.
I want to interject a quick question.
Yep.
Was the client driving this? Was a policy driving this? How did this happen?
It was actually the client. It was the city of Issaquah, and they were looking for to do 3 pilot net zero energy projects. And so they did some housing. I'm not sure what the other one was, but then the fire station was one. So it was really policy and kind of a pilot proof of concept for the city and their climate energy mandates. So this is a station that's up the road. We looked at the bills. We did a level 2 audit, and they had and we were able to kind of break down where the end uses were by looking at the seasonal effects of the bills. There's an enormous amount of heat being used, and what we discovered is that the bay doors in the fire station, when they open and close, the standard design around here is to use unit heaters, which just heat the air. And so what happens every time you open the door, there's a call for a fire truck, you let out all that heat. Well, we took a different approach and used a radiant slab in those bays. And we got great results of that. And that's a great solution for those bays. But we can see some of the other loads here. I won't go into it. But here's the breakdown of what we found by looking at the stations. Most of them had continuously ducted central fan systems running 24/7. Most of them had ventilation at 3 times over ASHRAE 62. So, designers working on fire stations, they get nervous about, these are critical facilities. And so the safety factors start emerging. There's no heat recovery in a lot of these stations. There's electric heat on vent air, so really poor design choice. There's severely overlit. There was no occupancy sensors on the lights. These are 24/7 facilities, and the bay doors opening and closing with gas heated forced air. So these are kind of central systemic design approaches for fire stations. And with that, we get the results of that. And I'll show you kind of some regional comparative data. But another piece to this was right sizing the geothermal for space heat and cool and DHW. So this is a heat pump system that uses a geothermal heat pump. We were able to do a 12,000 foot fire station with 8 geobores, and we put them into the parking lot. We've served the entire building with 3 5-ton heat pumps. The base load is only 10 tons. And so we essentially put in 1 ton per 1,140 square foot. The typical rule of thumb when you don't do the calcs is 400 square foot. So we can see we've got almost 3 times, I guess, the savings in how much heat we used. And then we use radiant slabs, heating and cooling. And then the sleeping rooms get 4-pipe fan coils. Here's some site visits stuff. On the left is the drill rig. We're putting 8 bores into that parking lot. And then they feed into the building. This is the slab for the fire station. These are the 3 bays. Radiant floor on this entire project, both levels. Here's kind of a final shot of the project, a big cistern. We get plenty of rain up here. And then about 25 kW PV array, as well as some solar hot water. Here's the mechanical room. It's pretty tight. 3 ground source heat pumps, water-to-water heat pumps, and they serve domestic and space heat cool. So here's kind of the end result. Typical stations, we've got Seattle stations, there's Portland stations, Issaquah sister station that we modeled. EUIs in the 80 to 100 range, roughly. Fire Station 72 was an EUI of 29. After the solar, it's 23. So that's a great success story. But again, here's another design for off approach using those similar tactics. The radiant slabs, we did not allow any switching. There's seasonal heating, there's off, and there's seasonal cooling. There's no simultaneous except for the bedroom. So that's a big measure. Also, the heat recovery, ventilation, and the radiant floor are really big measures there to kind of keep fans off. Next project is the Sitka Library. This is located in Sitka, Alaska. We did 3 projects up there, all 3 set out to decarb. This project in its previous state was about 8,000 square feet. It got bumped up to 12,500 square feet. It was it had a very large fossil fuel. It had a very large heating oil load. About half the energy of the previous station was using heating oil. So the city of Sitka wanted to get off of that, because off of importing diesel into the state, because they had just built a brand new hydro dam just outside of town. So this project was kind of a deep green retrofit. We put 4 inches of insulation around the entire envelope. It's all triple glazed windows. That's kind of standard, par for the course in Alaska. All the architects are really good at designing very well insulated buildings up there, because, well, they have to. And the outcome here was, or the result here was, the EUI was 99 and we brought it down to 32. So this is a pretty big reduction. And architect was MRV Architects out of Juneau. They did a great job. Here's the old fire station. It was in need of repair. The roof was starting to fail, so the usual story for upgrades. There's plenty of buildings out there that are in the same state, so keep this in mind. Here's the kind of a shot with the sound in the background. Here's why people come to the library. This floor inside, so we put in a radiant floor system throughout. It's only doing heating. We don't have a cooling load in this climate. Gorgeous view out here. Again, triple glazed windows. R20 on the outside of R15 inside of the metal stud wall. R60 roof. And the slab, we poured a topping slab on top of 4 inches of insulation. So it's very well insulated. Over to the left, we can see there was a giant duct running down the middle of this library. We took that out, so there are no ducts anymore. We're using high throw diffusers, kind of scattered around. This was the old heating oil boiler that got pulled out. You might have to squint here. This is the new system that got put in. Down to the lower right, we can see 2 VRF units. We've got a little hood on the top to kick the air out, because it was blasting at this under pin, and up there icicles were a concern, and so we had to route around these icicles that would form. Inside the room, here's the indoor hydronic units. These are refrigerant to water heat exchangers. There's a buffer tank, and then here's the manifolds for the radiant floor. So this entire project is being heated with a VRF unit converted to hot water. And so we're heating the floor with about 100-degree water. Down lower left is a really highly efficient ERV made by BPE. It doesn't have any fans on it. You kind of build it and assemble it. But these can run 85% plus sensible recovery. And they're pretty slick for tight spaces where you can put the heat exchanger and you can remote the fans and filters. All right, so here's another
before you get into
yes.
it, though,
Yep.
it's like a good complicated graph here. You
Yep.
are at time.
Oh, I am.
So
Okay.
you should summarize it a little bit more, or that.
Yeah.
Or
Okay.
place for questions. Your stuff is amazing, by the way. I'm totally wrapped with attention.
Okay. Well, I'll give me 5, and I'll wrap it up. Okay. So let's see. Here's the before and after. Oil and electricity. We can see we eliminated all the heating oil. That's the left. Interesting on the right are this temperature regression modeling. So we put the bills in before and after, and we can see the slope of this outdoor temperature dependency EUI. And so previously the slope was really steep. When we super insulate, the slope comes way down. And so that's a really critical piece of when you've kind of achieved a high performance envelope, is you've reduced that EUI and the heating nuts. Here's how it compares to other libraries. West Side School, I'm going to go fast. Let's see, EUI 14. So this converted a church to a school. It's one of the lowest energy use schools at 14 EUI. There's the church. There's in process. Here's the new space. Very simple systems, ductless heat pump, energy recovery ventilation systems, operable windows, low LPD, and then a ceiling fan to distribute to air. Here's some energy use. Knocked down all of here's the before and after. They had another school, so it went from 45 down to 14. HopeWorks, I've talked about this. This is a net zero energy project. It has heat pump water heaters on individual stacks, so it runs down. 200 kW of solar for net zero. Eliminated the corridors here, and so there are just exterior corridors. It's a courtyard setup. There's some exterior rigids, some triple pane windows. There's the sand-ins stacks on the roof. There's the tanks, and then those route down to 3 sets of units. Blomberg dryers, passive ERVs, more solar. So here's the, we just kind of started that project, but 2020, we're net positive by 124%. So good news so far. We'll see how the winter goes.
Hold the presses there. Get back there.
Yeah.
So am I seeing a 5-story tall building?
4, yes.
Well, I got a
Parking's under level, yeah.
lights, fans, some mechanical alarms, all that kind of stuff.
Yeah.
Okay. And it's net positive at 124%. We were just having a chat yesterday about what was sort of technically feasible. So I have to applaud you. Like, all right, man. Well done.
All right. So here's more of the design for off kind of rolled in. I didn't talk about these, but just trying to make the point that, taking this approach on your existing building can net low EUIs. And these are the UIs that we need to get the existing building market down to in order to make room for additional loads as we start to decarbonize. And that will wrap it up.
Woo! That's amazing. So thank you for leading us through that, Shawn. That was so cool.
Yeah.
If anyone wants to put comments in the chat, let me read through. There's a debate over whether or not there's such a thing as over geeking. Probably not. The people were saying like, hey, is there gonna be a recording of this? Because I know a lot of people wanted to review this carefully to see like your specs, your energies, share it with some folks. This one, Carl Johnson wants to know, what about air quality and ventilation, especially with the fires? How are you dealing with that in your designs?
That's a good question. We've had it come up, especially on our low income apartment work. And, obviously up here, it's not, we have mostly been getting the residual of your fires. We are working on some projects down there, but, smoke is a really difficult thing to filter out. And I think, the consensus on that is, about MERV 13. You can take it higher, but there's energy penalties on that. But this smoke stuff is a whole different sort of category and response. And I've worked on casinos HVAC systems before for tribes that allow smoking, and so we can get really carried away with these zapper, electronic air cleaning catalytic processes, and those will strip smoke out. They can strip pretty much anything. But they're spendy and they're not really appropriate for residential. But there are some products that can deal with the smoke, and they do it by charging the particles and grabbing them. But this is all kind of new territory, as well as what do we do about COVID, right? And that's another spin off of some of this stuff. Obviously having operable windows. That's getting more air, and that seems to be one of the responses in our buildings is allowing more outside air in. But in terms of kind of systems and what we can do, there's strategies, move more towards displacement, ventilation versus mixing. That's another strategy. There's UV treatments, but I think the science is still a bit early on a lot of this stuff, especially at scale and especially in smaller stuff. So I think it's a great question. It needs some attention.
Like rapidly, we're in our 4th year of a fire season, like a prolonged, dangerous, kills people, like my mother-in-law, right? If you got impaired lungs, it will kill you, right, for real. So it's like, yeah, we need some good answers on this. The zapper technology that you use for smoking in casinos, that's interesting. So that's how you do it basically, huh? You have to like that or electrically charge the molecules, but one way or another use electricity to either track them or destroy them.
Yeah.
Okay. Yeah, that's an energy use. Maybe worth it for health.
Yep. So is bumping up your outside air. That's what Seattle has done. They bumped their outside air up to 50%, and the energy use in the summer went up by 700%. So there are trade-offs to more air.
Wow.
Yeah.
Okay. There's another question about Ram. Narayana Murthy over at EPRI, who said, "Hey, Shawn, heard a lot about Washington's law against fuel switching. Can you comment on how to overcome that?"
Oh boy.
Well, briefly, I guess. There's more
Uh,
questions.
no, I mean, I don't have a lot. I mean, there's been several runs at carbon taxes, and those, you know, the money kind of won over on those ones, but the lobbyist money. But I think, you know, when this was brought up, it was probably a year or two ago, maybe a year ago, and I think there was consensus that just the industry wasn't ready. I mean, that was kind of the argument. But
Mhm.
that said, um, you know, the city of Seattle has just basically written a new code that basically makes it really hard to use gas, and I think that is really the response that the city took.
Mhm.
Um, and so they're really, you know, grabbing onto the emissions. And before it was about cost effectiveness, but now that the game is carbon and emissions, um, you know, you have different arguing points, as you guys, as California is aware. Um, but yeah, I think that has been how the policy is moving forward. So, you know, for example, the next code in Seattle, you got to use heat pumps in apartment in R2, and you've got to use heat pump water heating. And so they've just said, we're not, you know, you can't use gas.
Oh,
And so
there you
that's how
go.
they've done it. Yeah. So it's happening. It's just the, you know, doing it where you just outright ban the gas was not very popular. And I think that has been
So
seen down in, down
instead,
in
they're saying
California.
like you're allowed to still cook with gas, if I'm hearing you correctly.
That's
Like,
right.
so you have to put a lot of money in for the luxury and danger of a gas range, which I imagine that's a discouragement enough that some developers just don't put in the gas stoves, while other ones perhaps do, right?
Right. Yeah, yeah. And there's, you know, I had heard some proposals about, you know, requiring sub meters for each unit for
Mhm.
gas. And so once you do that, then the costs are so high that you go back to electric. So I mean, that's, you know, that's one approach. But yeah, I mean, the cooking for gas, cooking with gas in our multifamily stuff is pretty rare, except for kind of high end residential. But in the low income and kind of market rate stuff, it's mostly all electric anyway, just because of cost.
Now that's interesting because, you know, this afternoon we're going to hear from Mazi and Danny from the
Yeah.
Energy Commission about the 2022 code.
Oh,
And the Energy Commission can't ban gas stoves, but we could do that through CalGreen, but they can't. At least I don't believe they could. Even if they could ban gas in domestic hot water and HVAC, which they might take a code measure that makes it really expensive, or they might take a code measure that makes it non-legal, but we still have to deal with gas stoves. So my question is, what you're saying basically that's maybe 90% will be going all electric as a consequence of this prohibition on gas, water heating, and space heating. Did I hear that correct?
yeah, for R2, for multifamily.
Multifamily.
Yeah. So the other sectors, it's a different game, and you know, I would say that the use of gas, you have to, you know, we have a process up in here called TSPR, and it is essentially looking at you have to meet an energy and emission budget on your project, and so you do this modeling in SD phase just to determine if you can even use this certain fuel type. And so once you kind of look at it, there's a limit to how much you get. And so by running that extra exercise and having that policy in place, then the codes can actually ratchet down the amount of emissions. And so that becomes the mechanism at which you can kind of force decarb.
Okay. So this is, yeah, we're going to see if hopefully our code follows yours, at least for multifamily, which seems like the strongest chance because our single family developers are the ones who had to deal with putting in solar in the 2019 code. And so they're chapped on that topic and they want to not have to do anything more for climate change in the next code. So generous of them.
Hey, Sean, if I can add something, right?
Yeah.
So we had a developer who, I mean, it was a small development, but they paid, because they had to run a small gas line extension, they paid about $15,000 per home just to run the gas line, just
Wow.
for cooking, right? It was already heating, heat pumps, heat pump water heaters, easy, right?
Wow.
Cooking, they were willing to pay that much. But one of the things they said was it took so long to run the gas line extension and it held up their development for a few months. It's single family, right?
Right.
That going forward, they're going all electric on all their rentals or all their multifamily. But they still have a hesitation about getting rid of gas rooftops in single family.
Yeah.
Well, that's really interesting information, though, to hear what the price is for them. A $15,000 gas stove.
Right.
But, you know, we talk about
Oh, that's before the gas stove, right? That's
I
just
know,
for
no,
the
but it's essentially
yeah. It's like a $20,000 gas stove.
it's an dang. People don't understand that that's what their gas stove costs. That it's like $15,000 plus its purchase price and its installation cost. So it's, you know, like an $18,000 gas stove. And they have to pay a mortgage on it, so it's double that. It's about a $36,000 gas stove over their 20-year mortgage. That's effing insane. So I'm gonna move you to chat because I have to go make lunch for my family. But you guys are welcome to continue to talk here. I'm not gonna close it down. And it's Shawn. I'll just give you one more like, woo! Thank you for leading the way up there. I hope you see Alice Sung is really interested in your school example. And she is our strongest proponent of electrification and solarization of schools in California, bar none. And if you could help her out by like posting where your case studies are, because I bet you have these up online on your website, perhaps.
Yeah.
A lot of people would be happy to use them. That'd be great.
Okay.
If you put that in the chat.
Okay, we'll do.
Thank you, Shawn.
Shawn, I have a question. This
Sure.
is Tanya.
Okay.
You go. I'm gonna go to lunch. You just keep on talking.
All right. Thanks.
Thanks, Shawn. Other Shawn. I'm super excited about your work. I've been following it. One question I had though is you were talking about the code. Are you talking about the new building code in the state of Washington that's starting in like 2022, or are you talking about like the executive order from the city of Seattle that requires that their municipal buildings not replace fossil fueled transit and building systems with fossil fuel? They have to replace it with electric if they do a major upgrade. So I'm like, what code are you talking about?
Okay, yeah, that's a good question. I'm talking about the new Seattle energy code. And so what the codes that you mentioned, so the city of Seattle's policy on, you know, when you get to end of life on gas, you got to swap it to electric. That's been a policy in place for several years. But the new code that I was referring to is the Washington State Code, and then the kind of I guess the next more aggressive step would be to the Seattle Code. The Seattle Code's always been a little step ahead of the Washington Code, and that is the one that I was sort of mentioning referencing in the presentation.
Okay, thanks. I was just like, which one was he? It's been hard to track all the changes. There have been so many over the past couple of years. So thanks.
Yeah, I mean, this round of code is one of our most aggressive rounds in Seattle, and so it's having a lot of debate right now, and it's been delayed now twice. So it was originally supposed to go in play in November. And then they moved it to February, and I think it's even moving further, but I think that's more, you know, COVID recession related than anything. But there's been plenty of, you know, the same sort of arguments that we've been seeing in the decarb movement in, you know, California.
Yeah. Are you, you know, I know that they did push forward to the CT2045. I don't know if you were able to make it for my presentation on freeing up the data. Any thoughts on how that's going? The whole data at device, data standardization, communication control, so that we can, you know.
Yeah, I mean, I think the you know, I mean, the stuff that I know about, you know, ductless heat pumps and some of the integrated, shall we say, residential heat pump water heaters. I mean, there are products now that have that port in it. So I think that, and there's, you know, been several pilot studies that have been done. BPA has been working with several folks. They just did a big pilot study on demand response and using the CT2045 protocol. But that work is sort of happening. We're looking at it now with the work we're doing with the kind of the new class of heat pump water heaters, the low GWP stuff. And so that, you know, there's a lot of sort of momentum on getting those communication protocols in the equipment now. That's where a lot of the focus is. But in terms of, you know, bigger equipment and the rest of the industry, I don't really know a whole lot about, you know, what the other manufacturers or equipment are doing.
Yep. Thanks.
Yeah.